In this example problem, we will design a singly reinforced rectangular concrete beam with the span and loading shown. And in this example, our self-weight will not be given. Our first step will be to compute the factored design moment and then find our MN required. So for our live load, we can find our moment diagram, which will be linear up to our first load point, linear across, and then linear down to 0. And our maximum here will be 240 kip feet. Since we aren't given our section, we're going to need to make some kind of estimation or assumption for our cross-section shape to find our dead load. So we can estimate our height using two different methods. The first would be a rule of thumb, and this rule of thumb says that our height is equal to our length in feet, and this will be in inches. So for us, we have a length of 24 and 6 is 30 feet, and turn that into inches. So we'll start with a height of 30 inches. And we can remember from our past examples, we can assume that our base is about equal to half of our height. So we can start with a B of 15 inches. The other way that we can estimate our height is using ACI 318.14 and the minimum thickness requirements, which are there for serviceability purposes. So the minimum thickness requirements in ACI tell us that our height needs to be greater than or equal to L over 16 for a simply supported beam with a normal loading. So for us, we'll have our H needs to be greater than or equal to our 30 feet divided by 16 times 12 inches per foot, which will give us a height of 22.5 inches. So I'm going to round up and say we'll need a height of 24 inches, rounding up by 2 inches. And then we can find our B equal to 0.5 H, which is equal to 12 inches. Now for this example, we'll use the second approximation to see if we can get a smaller, shallower section. So we need to estimate now our dead load, distributed load. So for us, we have a 12-inch by 24-inch section. We're going to turn this into feet. So 12 divided by 12 inches per foot squared. And then take this times our concrete density, 150 pounds per cubic foot. And this will give us a distributed load of 300 pounds per foot, or 0.3 kips per foot. We can then use this to find our dead load moment diagram. And we'll remember it's parabolic with WL squared over 8 at the midpoint or midspan. So we'll have 33.75 kip feet. Our MU, which is our factored moment, is then going to be equal to 1.2 times our dead load, 33.75, plus 1.6 times our live load, 240, which will give us 424.5 kip feet, or 5,094 kip inches. So then we can use this to find our MN required, which is equal to our MU divided by phi, where we'll use a tension-controlled phi of 0.9, and we'll find our MN required here to be 5,660 kip inches. And this will be the moment that we'll move forward with through this example. So our next step is to select a row for tension controlled, and we remember that our row needs to be greater than our row min found from our ACI code requirements, and less than our row tension controlled, which we derived before, but using the ACI tension controlled limit of 0.005. So first, using our ACI expressions to find our row min, we can find our first row min value to be 200 divided by Fy, which we have 60,000 psi. So this will give us 0.0033. And then we have our other row min expression, so 3 times square root of our F prime C, which in our case is 5,000 psi, divided by our Fy, 60,000 psi, which will give us a row min of 0.00353. So we take the greater of these, which is our second one, and find that our row min is 0.00353. So next we need to find our row tension controlled. So we'll use the expression that we derived before, which I show here. And first, in this expression, we have beta 1. So we need to find our beta 1, which we'll use, or which we'll find using our code expression. So for us, we have an F prime C of 5 KSI. So the units I have in this expression will use KSI. So we'll get a beta 1 of 0.8. And we can see that our beta 1 is between 0.85 and 0.65. So we'll use our 0.8 for our beta 1. So now we can plug all of these values into our row tension controlled expression. So 0.85 times 0.8 times 5 KSI divided by 60 KSI. The units here cancel, so just make sure they're consistent. And then times 3/8. And we'll get our row tension controlled to be equal to 0.02125. So then we know that our row needs to be between 0.00353 and 0.02125. So we will start with row equal to 0.01, so 1%. And this is generally a good starting point. So our next step will be to use our MN required and an approximation of our MN to determine our B and D. So we'll start with our approximation. So we can approximate our expression for our nominal capacity by approximating our lever arm. So we'll say that our MN, and remember this is just an approximation, is AS Fy times 0.9 D, which is 0.9 D is an approximation of our actual lever arm, which is D minus beta 1C over 2. We'll then plug in our row BD for AS to get our MN equal to 0.9 row BD squared times FY. If we assume that our D is equal to 1.5 times B and plug in our values, we'll get 0.9 times our row, which we found and decided on the previous page, 0.01 times B times D, which we're going to plug in as 1.5 times B squared, and then times 60 KSI. We'll get a value here of 1.215 B to the third. We'll then set this value, which is an approximation of our MN, equal to our MN required, which we found before to be 5,660 kip inches. And we'll solve for B. And if we solve for B, we'll get our B cubed equal to 4,658 inches cubed, and then our B is equal to 16.7 inches. So we'll remember that our D is equal to 1.5 times B. So we'll get our D to be 25 inches. And now we're going to round our B, and we'll say we're going to round down in this case to go with a B of 16 inches. So our starting dimensions here are going to be a B of 16 inches and a D of 25 inches. So our next step is to use our cover requirements and an approximate bar sizes to compute our H and then our B. And then we're going to round our section to whole inches. So we're going to first assume that we're going to use number 9 bars for our longitudinal reinforcement. And we're going to assume that we're going to use number 4 bars for our stirrups. And we'll assume an interior cover of 1.5 inches. So plugging our values into our H, we'll have our D from our previous step, 25 inches. We'll have the diameter of a number 8 bar or number 9 bar divided by 2, the diameter of a number 4 bar, 0.5 inches, and our cover, 1.5 inches, to give us an H of 27.6 inches. So we're going to round this to the closest 2 inch. So we'll go to 28 inches. And we're going to say our B before was 15 inches, so I'm going to round that to the closest 2 inches as well, and we'll use a B of 16 inches. So these will be our final exterior dimensions of our section, and then we can use our H to back calculate our D, and we'll find that our new D is equal to 25.4 inches. So we'll use these section dimensions moving forward. The next thing that we're going to do is calculate our AS required and then select our bars and sketch our final section. So we'll start with finding our AS required. So our AS is equal to our row BD, so our row which we selected before, 1%, times our B, which we determined in our previous step as 16 inches, and our D, which we found in our previous step of 25.4 inches. And this will give us an AS required of 4.1 square inches. We'll then need to select the actual number of bars and size of bar that we'll use. So we can use a design guide, or we can just use our knowledge of bar sizing and determine the options. So here we can try 5 number 8s, 4 number 9s, or 3 number 10s, which will give us these different steel areas. So I'm going to choose 4 number 9s. I think it's the closest and easiest. We already assumed a number 9 bar, so we'll just move forward with our number 9 bars. So in this case, because we assumed number 9s, our D isn't going to change, so we'll still have a D of 25.4 inches. So then we can find our actual row, and our actual row is going to be equal to 4 inches squared divided by 16 inches times our D, 25.4 inches. And we'll find our row is equal to 0.0098, which still falls between our range of our row min and our row tension controlled. So we know that we're okay here. And then the final part of this step is to sketch our actual section, which I've done here, and we'll use this sketch in the upcoming steps. Our next step will be to check our cover and spacing requirements, and then we'll also check the final design strength. So the first thing that we need to do is check our required spacing. So our required spacing is the maximum of the diameter of our bar and 1 inch, and also 4/3 times our aggregate size, but we won't worry about that in our design. So for us, our bar diameter is 1.128 inches, so this is going to be our spacing. So we'll plug our spacing and our bar diameter into our two ACI design checks. So our first, we'll have 2 times 1.5 inches for our cover, plus 2 times 0.5 inches is the diameter of our stirrup, plus 4 bars at 1.128 inches, and then plus we'll have 3 spaces between the bars, also at 1.128 inches. So we'll find this to be equal to 11.9 inches, and this is less than our B of 16 inches. So our first check is okay. So similarly, our second check will have 2 times our cover, 1.5 inches, plus 2 times our stirrup, 0.5 inches, assuming a number 4 bar, plus 2 times our bend diameter, which is 4 times the diameter of our stirrup, so 2 inches, plus our n minus 1, so 3 times 1.128 bar diameter, plus 3 times our spacing, 1.128 inches, to give us a value of 12.8 inches, which is still less than our 16 inches. So we're okay with both of our checks. We'll be able to get all 4 bars in our section width with the proper spacing in between the bar. We will next check our actual nominal moment capacity. So first we'll need to find our beta 1, which we found before is 0.8. And then we can use equilibrium to find our compression block depth. So our C is equal to 4 square inches, 60 KSI, which was our tension side, and then the remainder of our compression side, 0.85 times 5 KSI concrete times 0.8 beta 1 times our B of 16 inches will give us our C of 4.41 inches. And we can remember that our A is equal to beta 1C. So 0.8 times 4.41 will be 3.53 inches. So then we can plug these values into our expression for our nominal moment. So we have 4 square inches, the area of our steel, 60 KSI, the yield strength of our steel, times our D, 25.4 inches, minus A, or beta 1C, 3.53 inches, divided by 2. And we'll find our nominal moment to then be 5,672 kip inches. So we can also check the strain in our steel. So 0.003 times our D, 25.4, minus C, 4.41, divided by our C, 4.41 inches. And we'll get our strain in our tension steel to be 0.014. So this is much greater than our tension controlled limit and will be out in our yield plateau region and maybe even the strain hardening region. So we're okay here. We also need to check our MN required, which was 5,660 kip inches. And we can see that our MN provided is greater than our MN required, so we're okay here as well. So our final step is to revise our self-weight and if it's needed, and check our capacity. So we'll find our self-weight is now our new section dimension, 16 inches by 28 inches. We'll divide by 12 inches per foot squared to get our units consistent, and then take it times 150 pounds per cubic foot. So we'll get our new distributed load to be 467 pounds per foot, or 0.467 kips per foot. We will then use this new distributed load to find our new self-weight moment. So our W, 0.467 kips per foot, times our L, 30 foot squared, divided by 8, will give us 52.5 kip feet. And then we can find our new MU. So our MU being equal to 1.2 times our dead load plus 1.6 times our live load, which will give us 5,364 kip inches. We can use this to find our MN required, which is 5,364 kip inches divided by 0.9, our phi factor assuming tension controlled, which will give us 5,960 kip inches. If we compare this to our MN provided, we'll see that our MN required is greater than our MN provided. So this means that our section's no good. So we're going to need to go back and revise our section. The easiest and quickest revision is just to increase our steel area. So what we're going to do is we will try using 5 number 9 bars. We'll next need to make sure that we have the capacity we need with our new design, our 5 number 9 bars. So we'll do that by finding our new nominal moment capacity. So our C is equal to AS, which now we have 5 number 9 bars to 5 square inches times 60 KSI divided by 0.85 times our F prime C 5 KSI times our beta 1.8 for 5 KSI concrete, and our B is still 16 inches. So then we'll find our C to be 5.51 inches, and our A is 0.8 times 5.51, which will be 4.41. So then we can use our A and our C to find our MN. So our MN is 5 square inches times 60 KSI times our D is still 25.4. If we had changed our bar size, then we would need to check this, minus our A, 4.41 divided by 2, which will give us our MN equal to 6,958 kip inches. So we can compare that to our MN and see that it's or significantly greater. So we know we're okay. So our design is strong enough now. We also need to check and make sure that we're still tension controlled. So we'll do that by finding the strain in our steel. So 0.003 times our D minus C, so 25.4 minus 5.51 divided by 5.51 gives us 0.011. So we're still tension controlled. The last thing that we need to check is we need to make sure that we can get all 5 bars into our beam width. So we'll do our 2 ACI checks again, which I've written out here, and we'll see that both checks check, so we're okay. So that completes our design. So we can see our final design has a height of 28 inches, a width of 16 inches, and 5 number 9 bars for our 5 KSI concrete and 60 KSI yield strength section.